get started. We are going to do, oops, my camera was in a funny position. I'll probably be doing that later with you lot as well. Can you see the top line? Do I have to move this around a little bit more? Up and good, it's more. Yeah. You see the top line? Everything good?
Yes.
Okay, let's get started. There are 3 homework questions from, is it 2.4? Yes, it's from section 2.4. So, and I promised you that we would do them together, and we are. The only difference is that some of these numbers are going to change because that's the way WebAssign does. But essentially, they take that definition that we gave you yesterday and they draw a picture and they're asking you to find what delta would be. So let me tell you what delta is. Delta is the distance from the center, in this case 4, to here, and delta is the guy from here to here. Now, if these are the same, right? So if that distance is the same as that, then that's delta. But if this is small and this is big, delta is always going to be the smaller of the 2 choices. So delta is the smaller of the 2 distances. And that's all they're going to ask you to find deltas. So let's see what this picture looks like. You've got y equals the square root of x. Over here, you've got 2. Over here, you've got 4. So at 4, the answer is 2. That's pretty obvious. And this picture is actually proving that the limit as x tends to 4 is 2. Now, up here, you've got a 2.4 and a 1.6. And here you've got 2 question marks. So what we're going to do to solve this question is we're going to find out what value of x this guy is, and then what value of x this guy is. And once we know these, we'll find out what the distance from 4 to there is, and what 4 to here is. And whichever one of them is the smallest, we're done, right? So let's see how that works. Since I know the function is y equals the square root of x, if the y is 2.4, then I put 2.4 in here, and then I solve for x, and to get x, you square. So 2.4 squared, and the answer is 5.76. So I know this guy here is 5.76. And then I'll get this one there. So I'll start off with the function. I know that the y value is 1.6. Now I'm going to find out what x value would get you a 1.6. And I get that by squaring. And if I go 1.6, oops, clear that. If I go 1.6 and I square it, I get the answer 2.56. So this guy over here is 2.56. So let's see who delta could be. If you go from 4 to 5.76, delta might be 1.76. If you go from 4 to here, the distance between 4 and this number is what, 1.44. And the smaller of them was 1.44. And we've just answered question 1. So delta is the distance from the value of x4 to the outside, and it's the smaller of the 2. And what the precise definition says is that if you want to get an answer somewhere between here and here, as long as you go 4, give or take 1.44, everybody in that band will stay inside that tolerance. And that's question 1. While you're figuring that guy out, let's look at question 2. Question 2 is even easier, I would say. You've got a function that looks like that. They don't even tell you what the formula is because you don't need to know. Right in the middle, you've got 1. And going over here, you've got 1. And then you have a 1.2 on this side. And that ends up being 0.7. And then you have a 0.8 on this side. And that ends up being a 1.1. Don't worry about the scale because it is totally wrong. Delta, which is the only thing you're being asked to do in this question, is already pretty much done for us. The distance from here to here is 0.1, and the distance from here to here, whoops, is 0.3. And delta is the shortest distance from the center to the two outside guys, and so delta is 0.1. So from this value of x, going left and going right, the distance from the center to here is a candidate for delta. And you have two choices in this case, and you always pick the smaller of the two to be delta. And that's the second question done. And we are now going to have the world record for the quickest section of homework ever done, because our last question is this one. In this question, y equals x squared. They have very little imagination. I'll stick to my color scheme. This is one, and that is one. And then we're going to go 1.5 and 0.5. 1.5 takes you to here, and 0.5 takes you to here. And our job is to find delta, and delta is the distance from the middle to here, or the distance from the middle to here. Okay, you have got 1 minute. Go for it. You find delta first, and then I'll do it. Everything you need to know is here. And kind of do it like question one. And 3 decimal places. Okay, that's it. Let's try it out. Okay, already kind of done the first one. This is it. When x is when the y value is 1.5, we're trying to find this question mark, this x. So y equals x squared. 1.5 equals x squared. To get x, you take the square root. And so on this side, it's 1.225. So the delta, the distance from here to here, is 0.225. Now, if you go the other side, you're going to have y equals x squared again. But let's find out what happens when the y coordinate is 0.5. Well, the square root of 0.5. And the square root of 0.5 is in fact 0.707. So I now have on this side 0.707. And the distance from the middle one to this outside point is 0.293. So it could be 0.225, it could be 293. The smaller one is 0.225. Hopefully you got that. That's the only real question that you would deal with. Essentially what this is saying is, look, if you want to be within 0.5 of the answer, you just need to make sure that you're within 0.225 of 1. Now, what we can then do is you can shrink this down to virtually nothing, right? You could make this fella here essentially epsilon, what we call it, 0.00001, right? So you're only going to be from 0.9999 to 101. And no matter how much you shrink that, you'll always be able to find a delta, which is a little range of values here, either side of 1, where everybody in that range will be inside the answer that you are willing to live with. And that is us finished. Are you going to get a question like that in the test?
No.
No. Am I going to give you one in the final then?
No.
So we're good to go then, aren't we? Let's move on. Next section. So section 2.5. We're going to look at the idea of what's called continuity. So here is a formal definition of something being continuous. So imagine I have a nice function y equals f of x. And we are interested in what's happening at x equals a. Now, in this particular function here, nothing really that remarkable is happening. Would you agree that this function's limit at a is f of a? How do I know that? Well, can you see it's just a smooth curve with nothing going on? That's what continuous looks like. Most functions are continuous. You don't even notice it because that's kind of what functions should be, really. They should be continuous if life was fair. But here's the formal definition. A function is continuous at a point x equals a if, and there are two things that need to be true. The first one is that the overall limit as x tends to a of this function is a finite number. Technically, it has to exist. Well, so the overall limit has to exist and it has to be a finite number. That means it's not allowed to be infinity, right? It has to be 4 or minus 42, right? It has to be a number and the overall limit has to exist. And the second hurdle is that this overall limit as x tends to a of this function has to be equal to the value of the function. And if that is true, you are continuous at x equals a. So now we're going to look at what is called discontinuous. Or sometimes it's called not continuous. It's the same thing. So we're going to look at what kind of situations do you get where this isn't true? And there are three major kinds. So let's show you each one. this function is not continuous at A, right? It's discontinuous at A, if you want to use that phrase. So where does it fall down? Well, would you agree that this function doesn't have an overall limit? Because isn't its left limit a different number than its right limit? So it's not continuous. We call this picture, and I like this name, so it's not one I made up, someone else made it up. It's called a jump discontinuity. I kind of like that name, right? Doesn't the function kind of suddenly jump, right? It breaks value. Here's my next one. Right. So in this situation, it's not continuous at A either. And you might say, well, it looks pretty nice, but it fails under number 2. Isn't the overall limit of that function, whatever this height is, but isn't the value of the function actually different? And this has a name that I kind of like as well. It's called a removable discontinuity. Right, that's quite a common discontinuity for a function to have. This happens very often in piecewise functions. Do you ever see piecewise functions where for an x bigger than 1, it's this, and x less than or equal to 1, it's that? So you'll see them very often happen in piecewise functions. This kind of discontinuity tends to happen when you have a rational function where you can simplify it down, but there's still a little hole. Right. And the third and final one is this type of discontinuity. And if you have a vertical asymptote in your function, then at the point where the vertical asymptote happens, there's a discontinuity, and it's an infinite discontinuity. These are the 3 major types of places on a function where they're discontinuous. Jump discontinuity, removable discontinuity, infinite discontinuity. Now I'm going to add to this diagram some terms that sometimes are helpful. When you have a function that's kind of split into 2 like this side here is called the right branch, and this side here is called the left branch. In this case, there's a little hole, so this is the right branch, and this side here is the left branch. So whenever there's a discontinuity, and I want to talk about this piece of the curve, I'll just say the right branch, and can you see what I'm trying to talk about? I'm talking about this piece. If I say the left branch, I'm doing this. If it's a vertical asymptote, this side is the right branch, and this side here is the left branch. Now I'm going to share with you, I don't know if it'll help, but it helps me, a way of looking at a function and deciding if there is a discontinuity. And the way I kind of look at these questions is, I imagine that I'm driving a car. And if I get killed, there's a discontinuity. And the place I get killed is where that discontinuity is. So watch me drive this car. Would you agree the road suddenly ends and I hit a brick wall and I'm dead? I fall through a hole in the ground on my way to China. I'm dead. I zoom off into the atmosphere and die through lack of oxygen. Can you see that at each of those places, if you were driving from left to right, wouldn't something bad happen to you? And if something bad happens to you, there's a discontinuity going on. Now, these are not every kind of discontinuity in the world. There's lots of different ways you can break a function, but these are the three major ones. Are we comfortable about their names and what they look like and that they are discontinuous, right? So what we're going to do now is look at some graphs from the next section, which is why this thing was bent all the way down. So this one I'm bent. I don't know what I'm bending right now. Come on. That'll do. Okay. Forget about their questions. We're going to do my questions first and we'll come back and look at them. I want, just looking at this, I want us to get practice at identifying discontinuities. So I want you to look at this picture and I want you to tell me two things. I want you to tell me where there's a discontinuity. So you might, for instance, say there's a discontinuity x equals -2, right? That's the first thing. Tell me where it is. And then what kind it is. Wouldn't this be a jump discontinuity? Great. Okay, so I've done the first one. There's a jump discontinuity at -2. Volunteers now. Tell me about another one.
-4.
What's happening there? You're right.
Removable discontinuity.
Yeah, it's hard work to say until you do it a few times. I like the names. Doesn't removable and jump and infinite kind of make sense when you see the picture? Okay, we've got some more. Okay, I think we've got at least two
X
more.
equals 2, another
Tell me
jump.
another one. Agreed. Okay. We might argue about what to call x equals 4, but would you agree that there's definitely a discontinuity there? X equals 4.
One side's
I would
infinite.
go with the fact, yeah, exactly. That's what I would agree with Sabrina. I was going to say that. It looks to me like infinite. Yeah, you could argue it's a jump, but I would say infinite is more realistic. We comfortable with that? We feel, if I show you a picture, because I'm going to show you another one in a moment, we can talk about what kind of discontinuities it has. Okay, same question. Tell me where it is and what kind of discontinuity is happening there.
In -1, there's an infinite discontinuity.
Agreed? Agreed? There's at least 3 more to go.
At 1, there's another kind of confusing one. Would you say that's a jump or a
It's a jump.
A jump discontinuity.
Yeah, it's a jump. There is a removable one, but it's not at x equals 1. Can you see? It might be hard to see because it's very tiny in this graph. I can see it, but my screen's pretty big. There is a removable
Yeah.
discontinuity. At -2, it's so tiny you might not see it, but there's a little hole there. Do you see it? Right. And where's the other one? I know there's another one. Yes, there is one more we haven't talked about yet.
You get to jump at 0? Or is that a jump?
Yeah, there's another jump discontinuity at 0. So infinite, removable, or jump discontinuity, right? They're very specific points on a graph where something bad is happening, right? Now, before we move on. Hey, I'm getting better at doing that. Let's show you nuances. There's a fancy, that's probably a French word. Nuances on those types of situations. That is a removable discontinuity. Agreed? That's a removable one. Isn't that also a removable discontinuity? You don't need to have that dot. It might be there, it might not, right? And in fact, isn't that dot telling you the value of the function at A? Right, that solid dot there. This is removable, so is that. Why do I like the name removable? If I pick this dot up and actually put it where the hole is, wouldn't the function be continuous now? If I said the value of the function was here, essentially what I would have done would have been that. And if you fill in the hole in the road, I don't get killed anymore, so it's continuous. Now, that's a little nuance on removable. You agree that's a jump discontinuity? Is it not a jump discontinuity? Is it not a jump discontinuity? And isn't that a jump discontinuity? So what am I getting at here? Do you see that little solid dot that's present in at least 3 of these? That's where the value of the function happens to live, right? That's what f of a is equal to. For a jump discontinuity to be a jump discontinuity, can't that dot belong to the left branch, to the right branch, to none of them, and the value of the function somewhere else, or not even have the value of the function at all anywhere? They still all count as jump discontinuities. Great. Now, there's not really many nuances on an infinite one, but would you agree that's an infinite discontinuity? Would you agree that's an infinite discontinuity? And would you agree so is that? So if you see a vertical asymptote, aren't you going to have an infinite discontinuity? Right, so there's not really a nuance on that. They're just basically different versions of vertical ones. And that's us covered what a continuous and mostly what a discontinuous function looks like, right? So far, so good. So I'm not doing it unless I need to. But if I gave you another one of those graphs, do you feel comfortable you could identify where all the discontinuities are and give me a name? There's a jump at this, there's a removable discontinuity at that, and there's an infinite discontinuity at some other place. Do you feel comfortable about giving a graph? Tell me where those things are. Okay, we can move on then. So now, or can we? Question. Are we good? Okay, so you might think everything is finished, but they're not. There are 2 more concepts. We're going to look at right continuous and left continuous. So you might have a function that's not continuous, right? We call that discontinuous, right? We've talked about all the permutations of that. But we are allowed to have a thing that's called right continuous and a thing that's called left continuous. Let me show you what that looks like. Its definition. A function is right continuous at a point x equals a if the following two things are true. And where's my other guy before I write this down? I want to show you by just putting it back on the screen here. There's that guy. Right. A function is continuous at a point x equals a if the overall limit is a finite number and exists, and secondly, if the overall limit is equal to f of a. A right continuous is a kind of reduced version of this. So a function is right continuous if the limit as x tends to a plus of f of x, right, exists and is a finite number. Don't we call that a right limit? Remember, x tends to 1 plus, we call that a right limit. And the second property that has to be true is that the limit as x tends to a plus of f of x has to be the same thing as the value of the function at a. So, can you see the definition of an overall continuous and a right continuous are very similar? So what do they look like visually? Well, let's take this fella as an example. Would you agree that this has got a jump discontinuity at x equals a? It also has the property that it is left continuous. Do you see where the dot is? It's on the left. Now, that would be left continuous. And right continuous would look something like this, which is probably the one I should have done first. Would you agree that this function, I don't know why it's wobbly in the right, but would you agree that the dot is on the right branch? Right continuous. Here, the dot, which means the value of the function, is on the left branch, so it's left continuous. And here, the dot is on the right branch. So sometimes a function is discontinuous, right, for whatever reason, but it might still exist as a left or right continuous. So we're going to go back to those two graphs that we had earlier, and we're going to see if we can identify any places where it might be, oops, I just pressed a button which I don't know what it did. Has anything bad happened on your side? Because I accidentally pressed a button up here and I don't know what it did. Okay, if within the next 10 seconds nothing blows up, then I dodged a bullet. Okay, here's our guy. So let's look at x equals -2. Right, let's look at this jump discontinuity. If you're going to get left or right continuous, you probably want to look at places like this. Is there a left or a right continuous at x equals -2?
Left.
I didn't catch that, Skylar.
Left continuous.
Gotcha. How about at x equals 2? Left or right continuous?
right continuous.
Okay. How would, you're right. Could you explain that? Maybe you could say it in a way that might click for some people, because I'm seeing some puzzled faces still.
Because it's got the filled in dot on the right hand side.
Okay, so the right-hand branch has a filled-in dot. It's right continuous. The left-hand branch. Now, when I talk about left and right, do you know it's an isolated picture? Right, so when I'm interested at x equals -2, isn't this side the left branch and this side is the right branch? But when I move to this guy, you see how this is the left and that is the right. So if you're wondering what I'm calling left and right, depends on where I'm looking. Okay, let's look at x equals 4. Right, left or right? Because it does have one.
Right.
Agreed. So if we agreed that the easiest way to tell is where the solid dot is. If it's on the right branch, it's a right continuous. And if it belongs to the left branch, it is left continuous. I think that's probably an easy way to remember. Right. Because we're almost finished this. Okay. X equals 0, left or right?
Left.
Agreed. I'm not quite sure how to phrase this. What is happening at x equals 1? Left, right, or nothing?
Neither.
Thing.
Yeah, neither or neither. Can you see why it's a neither or a neither? Isn't the dot not in either of the branches, right? It's just floating out there in midair. Okay, in that same vein then, what's happening at x equals -2? Is it left continuous, right continuous, or neither?
Neither.
Okay, it's a removable discontinuity, isn't it? But it doesn't have a dot on the left or the right branch. Now here's something we haven't talked about, but does exist. Look at x equals 3, right? Way over the end there, right? X equals 3. Left or right continuous? I'm not allowing neither.
It's left. What?
Agreed. There only is a left, but it's still left continuous. Doesn't that mean a function that, you know those functions that start and finish with dots? Won't they at least at the end have a left or a right continuous? For instance, what's happening at x equals -3? Left or right continuous? At x equals -3.
Right.
Okay, let's focus on it. Forget about everything. This is -3. Would you agree this is to the right of -3? Isn't this a right branch? And isn't there a dot there? But what about the left branch? Well, sometimes there isn't a left branch, right? It just isn't there. But it still counts as a right continuous. Okay, I guess to summarize what we've done today, do we feel comfortable about what a continuous function looks like? Just basically nothing's happening, right? But more specifically, can we identify the 3 major types of discontinuity, which are jump discontinuities, removable discontinuities, and infinite discontinuities, right? That's for overall continuous. And then a little subgroup, can we also identify when something is right continuous and left continuous? And we're getting a lot of nods there, which I like, because lots of nods mean, yep, I know how to do that. I feel comfortable. I could answer questions that ask me those kinds of things. We should finish on a joke then.